Okay, let's unpack this. Welcome to the deep dive, where we take a stack of your sources and really plunge in.
Find the good stuff.
Exactly. The key knowledge, the, surprising facts, the things that make you feel informed fast. Today, we're taking a deep dive into, well, the foundational knowledge for understanding how computers work.
And how to support them.
Right. Think of it like a shortcut through some really essential concepts. Maybe you're aiming for certification down the road, maybe not.
Or just want to feel more comfortable with tech generally.
Exactly. We're pulling insights from a pretty comprehensive guide, the kind you might use for CompTIA A spec.
Covers the whole spectrum.
Yeah, professionalism, hardware, software, security, fixing things when they break, all of it.
And what's interesting is how much of this applies beyond just fixing PCs.
How so?
Well, the problem-solving methods, understanding systems, even the ethics. It crops up everywhere these days.
That's a great point, even if you never actually open up a computer.
Right. There's value here regardless.
Yeah. Absolutely. It's about building that mental model, So let's jump in. We're starting, maybe surprisingly, not with the tech itself.
But with the person, the tech professional.
Yeah. What makes a good tech, according to this source? What stands out?
Well, it's a mix, really. Technical skills, obviously, but also the soft skills.
Like appearance, communication.
Exactly. Professional look, sure. But communication is huge. Not just explaining, but being assertive, respectful.
Assertive how?
The guide suggests validating the user's feelings first. So instead of just, what's wrong? Maybe start with, yeah, I know it's frustrating when this happened.
Builds rapport immediately.
Right. And crucially, try to avoid accusatory language. Like, steer clear of starting sentences with, you did, or why did you?
Oh, that's smart. Keeps it focused on the problem, not the person.
Definitely. And speaking of tricky situations, there's this great rule mentioned.
Mike's rule of confidentiality.
That's the one.
Yeah?
It's pretty blunt. Unless it's a felony or someone's in immediate danger, you didn't see nothing.
Huh. But vital. Right, given the access techs have.
Absolutely vital. Think about it. You're on someone's machine, you could see private emails, browsing history, anything.
Huge responsibility.
Immense. The source uses that sticky note password example. If it's a paying customer's machine, zip it. Respect privacy.
But if it's your own company's computer?
Then it's different. You might have a duty to report it based on internal security policy. So context matters, but privacy is key.
That makes sense. All right, so beyond the ethics, what about the actual process when something goes wrong? The troubleshooting.
Ah, yes, the methodology. This is core. The source lays out like a 7-step process.
Okay, walk us through it.
Step 1, identify the problem. And that means talking to the user, asking good questions.
Like the classic, has anything changed recently?
Exactly. New software, hardware, updates. Then step 2, establish a theory, a probable cause.
Not just a wild guess, though.
No. You use research. Google the error message, ask a colleague, check system logs or past repair records.
Got it.
3, test the theory. See if your idea holds water. Did that fix it or narrow it down?
Makes sense.
4, once you're pretty sure, establish a plan and implement the solution. Maybe follow vendor steps, use a specific tool.
Okay, fix implemented, done.
Not quite. Step 5, verify full system functionality. Don't just check the original problem. Make sure nothing else broke. And maybe implement preventative measures if you can.
Good point. And the last step?
6, documentation. Document findings, actions, outcomes. So important, but often skipped.
Why so important?
Well, the source quotes Santayana. Those who cannot remember the past are condemned to repeat it. Good notes save you or the next tech tons of time later.
That whole systematic approach feels calmer. Less panic, more process.
Exactly. And you're right, it's a skill you can apply to almost any problem, not just computers.
Okay, great foundation on the mindset. Now let's dive into the actual machine, the hardware.
The physical bits.
Right. Starting with the big one, the CPU, often called the brain, but the source says that's not quite right.
Yeah, brain implies intelligence it doesn't have. A CPU, the central processing unit, is really more like an incredibly fast calculator.
Billions of operations per second.
Yep. Simple stuff, just really, really fast.
Yeah.
The source mentions the old Intel 8088 to show the basics. Registers for tiny temporary data, a clock setting the speed, and the data bus moving info around. Like a highway.
So speed and data movement create the illusion of thought. What about modern CPUs?
Today, it's mainly Intel, AMD, and ARM. Intel and AMD dominate desktops and laptops, that whole x86-64 architecture.
What's the main difference between them?
Often how they manufacture. Intel historically did more in-house. AMD often designs and uses other companies' fabs to build them. So, fabless.
And ARM.
ARM is huge in mobile. Phones, tablets. They design low-power blueprints and license them out to companies like Apple, Qualcomm.
So that's why phone chips are different. Power saving is key.
Exactly. They throttle down aggressively to save battery, manage heat, different priorities than a desktop chip.
And the move to 64-bit processing, what was the big deal there?
Mostly RAM. 32-bit systems were stuck at accessing like 4 gigabytes of RAM. 64-bit blew past that limit. Essential for today's software.
Makes sense. And keeping these things cool is a whole thing too, right? Fans, liquid cooling.
Oh yeah. Thermal paste between the CPU and the cooler is crucial. And for the adventurous, overclocking pushing the CPU faster exists, but it generates more heat and risks instability.
Is there a safety net if you push too hard?
Sort of. Most motherboards have a CMOS clear function, often a little jumper or button, to reset the BIOS settings back to default if an overclock fails and the system won't boot.
Candy escape hatch. Okay, next up, RAM, random access memory. What's its job?
RAM is the CPU's super fast, short-term memory. It's workspace. It holds the programs and data the CPU needs right now.
Why random access?
Because the CPU can jump directly to any piece of data stored there almost instantly, unlike, say, reading a tape sequentially. Most RAM today is DRAM. Dynamic RAM.
Dynamic means?
It needs constant power and periodic refreshing to hold on to its data. Turn the power off, data's gone. Volatile.
And how is it organized?
Individual chips store bits, but they're put onto modules, sticks of RAM, that match the width of the CPU's data bus. Usually 64 bits wide these days.
Who manages all that data flow to RAM?
That's the memory controller chip, the MCC. It used to be on the motherboard, but now it's typically built right into modern CPUs for faster access.
What about RAM specs? Things like latency.
Latency, often shown as CL something, like CL16, is a measure of delay in clock cycles.
Yeah.
Lower numbers are generally faster, meaning less waiting time for the CPU.
And ECCM.
Error correction code. It can detect and fix small single-bit errors in the data. Makes it more reliable, so you see it in servers or workstations where data integrity is paramount, but it's usually a bit slower and costs more than regular non-ECC RAM.
Practical advice, how much RAM do you generally need?
The source suggests 8 GB is a minimum for Windows today. 16 GB is a good sweet spot for most people. 32 GB or more if you're doing heavy lifting like video editing, serious gaming, running virtual machines, assuming a 64-bit OS, of course.
Okay, so RAM's the fast workspace. What connects the CPU, the RAM, and everything else?
That's the motherboard. It's the foundation, the central nervous system, you could say.
Plugs into it.
Yeah. It's a big circuit board with printed pathways called traces that act like wires forming the buses. It holds the CPU socket, RAM slots, storage connectors, distributes power from the PSU, and provides the ports on the back.
Do all motherboards have the same features?
Not exactly. They all have the basics defined by the chipset, but manufacturers often add extras, built-in Wi-Fi, better audio chips, more USB ports, maybe RAID support.
And you can add more capabilities with expansion cards, right? Like graphics cards or network card.
Absolutely. Plugged into expansion slots, usually PCIe slots these days.
What's the most critical thing to remember when installing one?
Safety. Always unplug the PC from the wall outlet. Seriously.
Why is that so important if the PC is off?
Because even when off, many motherboards still have a trickle voltage, like a standby power. Plugging or unplugging a card with that voltage present can fry the card, the slot, or worse.
Okay, unplug first. Anything else?
Standard stuff. Make sure the card is compatible, use anti-static precautions, wear a wrist strap, or touch the metal case often to discharge static electricity. Then, install the drivers.
Ah, drivers. The software that lets the OS talk to the hardware.
Exactly. And getting the right driver is key. Using the wrong one is a common cause of problems. Windows Device Manager is your best friend for checking if hardware is installed and working correctly.
Good tip. That unplug it warning is definitely sticking with me. So motherboard connects it all, and it all needs juice from
The power supply unit, the PSU.
What's its main function?
It takes the high voltage alternating current, AC, from your wall outlet and converts it into the various low voltage direct current C voltages that your PC components need, like a translator for electricity.
Is knowing about AC/DC important?
It helps to understand the basics hot, neutral, ground wires. Useful if you ever need to test an outlet with a multimeter. The source also defines power problems, like brownouts, voltage sags, and blackouts, complete power loss.
How do you protect against those?
Minimum protection is a surge suppressor. It guards against voltage spikes. Better is a UPS, an uninterruptible power supply.
What does the UPS add?
Battery backup. It protects against spikes and sags and gives you time during a blackout to save your work and shut down properly. Highly recommended.
Okay, makes sense. Now, all those cables coming out of the PSU, what are the key ones?
The big one is the main motherboard connector, usually a 20 or 24 pin P1 connector. Then there's a smaller 4-pin or 8-pin connector, often called P4 or EPS12V, for extra CPU power.
And for drives and things?
You'll see SATA power connectors, thin L-shaped ones for modern drives, and older 4-pin Molex connectors still used for some case fans or accessories, maybe even a tiny mini connector for an old floppy drive, though that's rare now.
Can you use adapters if you run out of one type?
Yes, splitters and adapters exist, but you need to be careful not to overload a single cable coming from the PSU.
What about wattage? How big a PSU do you need?
Here's the key thing the source mentions. The PSU only provides the power the components draw. It doesn't force-feed wattage.
So buying a bigger PSU than you strictly need right now is okay.
It's actually often better. Running a PSU at, say, 50–60% of its capacity is usually more efficient, generates less heat, and can make the PSU last longer. Plus, you have headroom for future upgrades, like a beefier graphics card.
What's a good starting point wattage-wise?
For a typical new desktop build, something around 550 watts is often a reasonable minimum recommendation. Gives you flexibility. Also, look for efficiency ratings like 80+ bronze, silver, gold. Higher ratings mean less wasted electricity as heat.
Good to know. Anything else PSU related?
Just check the fan is working, if it has one, and ensure your case fans are set up for good airflow. Plugging them into motherboard headers is usually better than directly into Molex, as a motherboard can control their speed based on temperature.
That PSU wattage advice is really practical.
All right.
Okay, so that covers the core physical parts. CPU, RAM, motherboard, PSU. Understanding these is definitely step one.
The building blocks of the whole system.
All right, hardware sorted. Now let's move up a layer. The software that makes it usable, the operating system, OS, and how we interact peripherals.
Right. The OS is that essential bridge.
What's its main job, fundamentally?
It does several key things. It creates the user interface, what you see and click on. It manages all the programs you run. It organizes files on your storage drives. And it handles basic security, like user accounts.
And it dictates compatibility, right? Windows apps on Windows, Mac apps on Mac OS.
Exactly. They speak different languages, essentially, unless there's some kind of translation layer involved.
User interfaces, we mostly see the graphical ones now.
Yep, the GUI. Windows, icons, menus, pointer.
Like
clicky.
this.
The source notes how even GUIs evolve, like the Windows 10 Start menu versus Windows 11. Very different look and feel.
But there's another interface important for text.
Oh yeah, the CLI, command line interface, where you type commands.
Why is that still relevant?
Because sometimes the GUI breaks. If Windows won't load properly, the command prompt might be your only way in to fix things. Think Windows PowerShell, Windows Terminal, or just Terminal in macOS or Linux. Often CTRL-ALTT is the shortcut.
Mastering the CLI is like a superpower then.
Definitely a power move for troubleshooting, yes.
How does the OS keep track of all our files, documents, pictures?
It uses a hierarchical structure, like a tree, but upside down. Starts with a drive letter, like C in Windows, then branches into folders, then subfolders inside those.
And the path shows that structure, like C users your name documents.
Exactly. For techs, knowing the standard locations for things is crucial. Where are settings, Windows settings versus control panel, that ongoing confusion.
Yeah. Where do you find settings in Mac or Linux?
macOS uses system settings, formerly system preferences, and the utilities folder. Linux often uses Software Center apps and specific configuration files or tools.
Speaking of Windows settings, the source mentions the registry. Sounds important.
It is. It's a huge, complex database holding low-level settings for Windows and many applications, organized in a tree structure with keys.
Can you edit it directly?
You can, but you need to be extremely careful. Messing up the registry can stop Windows from booting. Always back it up before making manual changes. It's powerful but dangerous territory.
Noted. And the settings app is slowly taking over from control panel.
Yeah, it's a transition that's been happening for years, which means sometimes you find a setting in one place, sometimes the other, sometimes both. Bit messy, frankly. But key areas in settings are things like system, display, sound, power, privacy, app permissions, time, and language.
Good places to know. Okay, let's talk peripherals, the things we click in.
Input and output devices. Keyboard, mouse, monitor, printer. The most common connection now is USB.
So many USB types, though. A, B, C, micro, mini.
Tell me about it. And different speeds, too. USB 2.0, 3.0, 3.1, 3.2. The good news is it's mostly backward compatible. Plug an old USB 2.0 device into a new 3.2 port, it'll likely work, just at the slower speed.
What about cable lengths? Any limits?
There are practical limits for signal integrity. The source gives some examples. Old PITA drive cables were limited to 18 inches. Internal SATA is 1 meter. External SATA could go up to 2 meters. USB has its own limits depending on the version.
Good troubleshooting tip for USB devices.
Simple but effective. Swap things around. Test the suspect device in a known good port. Test a known good device in the suspect port. Helps you figure out if it's the device or the port that's the problem.
Makes sense. What other peripherals does the source mention?
Biometrics, fingerprint scanners, facial recognition like Windows. Hello. Very common now.
Touch screens.
Yep, built-in or standalone. The OS usually just sees them as a monitor plus a mouse input. They often have their own calibration settings.
KVM switches, what are those for?
Keyboard, video, mouse switch. Lets you use one keyboard, monitor, and mouse to control multiple computers. Super useful in server racks or test setups.
Must get confusing with all the cable.
Oh yeah, labeling is absolutely essential. And you need to know the keyboard hotkey sequence to switch between computers.
Game controllers too.
Sure. Joysticks, gamepads, usually USB or wireless. Need calibration, sometimes have force feedback settings.
What about sound? Built-in versus sound cards?
Most motherboards have decent built-in sound now, but dedicated sound cards still exist for higher quality or more connection options. The source touches on sound basics. Amplitude is volume, frequency is pitch.
And digital sound, sampling.
Right. Computers capture sound by taking snapshots or samples. Bit depth determines the accuracy of each sample, like 8-bit versus 16-bit. Sampling frequency is how many samples per second, like 44.1 kilohertz for CDs. CD quality is 44.1 kilohertz 16-bit stereo.
And you can get external audio devices too.
Definitely. USB audio interfaces, DACs, digital to analog converters, for better quality output, common for music production or audio files.
Video concepts, codecs.
Briefly, yeah. A codec is the algorithm used to compress and decompress video or audio data to make files smaller. A container, like a .mov or .mp4 file, is the wrapper that holds the compressed video, audio, and maybe subtitles. Just because it's a .mov doesn't tell you which codec was used inside.
Wow, okay. So the OS manages all this interaction through various interfaces and connections. It's a complex dance.
It really is. Understanding these layers helps make sense of it all.
Definitely. All right, we've got hardware, OS, peripherals. But where does our actual stuff live long term? Let's talk storage.
Where we save everything, our digital lives.
What are the main types of storage devices today?
Primarily, you've got hard disk drives, HDDs, the traditional spinning magnetic platters. Their speed is often measured in RPM, like 7200 RPM.
And the newer ones.
Solid-state drives, SSDs. These use flash memory, like in a USB stick, but much faster and more durable. No moving parts, so they're silent, use less power, and are much quicker than HDDs.
Flash memory itself is storage too, right? USB drives, SD cards.
Absolutely. Thumb drives, memory cards for cameras and phones. SD cards have different speed classes and ratings telling you how fast they can read and write data.
How do these drives connect inside the computer? You mentioned SATA before.
Right. SATA, Serial 8A, is the modern standard for internal HDDs and many SSDs. It uses thin cables, allows hot swapping, plugging, unplugging while the PC is on carefully, and has a 1 meter cable limit.
What came before SATA?
PATA, Parallel 8A, also called IDE. Use those wide gray ribbon cables. They were bulky, bad for airflow, shorter length limit, 18 inches, and no hot swapping. Big improvement with SATA.
Are there different ways that OS talks to SATA drives? AHCI?
Yes, AHCI, Advanced Host Controller Interface, is the standard mode for SATA drives. It enables features like NCQ, native command queuing, which helps optimize performance, and is required for hot swapping.
Important installation tip there.
Crucial one. If your system uses AHCI, make sure it's enabled in the BIOS C5 before you install Windows. If you install Windows in the older IDE compatibility mode and then switch to AHCI, you'll likely get a blue screen of death.
Ouch. Good to know. What about NVMe? Is that even faster?
Much faster. NVMe, Non-Volatile Memory Express, is a communication protocol designed specifically for SSDs. Instead of using the SATA bus, it connects directly via the superfast PCIe bus, the same kind graphics cards use. This dramatically cuts latency and boosts speeds.
And those often look like little sticks, right? M.2 drives.
Exactly. M.2 is a common form factor for NVMe SSDs, though some M.2 drives can still be SATA-based, so you have to check the specs.
So drive type, connection type, and communication protocol all affect speed. How do we organize the space on a drive?
Partitioning. You slice up the physical drive into one or more logical sections that the OS can treat as separate volumes.
Two main partitioning schemes, MBR and GPT.
Right. MBR, Master Boot Record, is the older style. It had limits maximum of 4 primary partitions. Or you could have 3 primary and 1 extended partition, which you could then divide into multiple logical drives. A bit convoluted. One primary partition had to be marked active for booting the OS.
What's the newer standard?
GPT, GID ID partition table. It's part of the modern UEFI standard that replaced BIOS. GPT doesn't have those same partition limits, supports much larger drives, and is generally more robust. It's the standard now for most new systems.
After partitioning, you format.
Correct. Formatting creates the file system on the structure that allows the OS to store and retrieve files. It also creates the initial root directory.
Common Windows file systems. FAT32 and TFS.
FAT32 is older, simple, very compatible, but has limits. Individual files can't be larger than 4 GB, and partitions are usually limited to 2 TB effectively. SATF was designed to overcome the file size limit, good for large USB drives. NTFS is the modern standard for Windows system drives. It supports larger files and partitions, file-level permissions, compression, and encryption. Windows usually requires NTFS for installing the OS or for partitions over 32 GB.
What's the difference between a quick format and a full format?
Quick format just deletes the file table, making the space appear empty. The data is still there until overwritten. Full format actually checks the disk surface for errors on HDDs and overwrites the data, making recovery much harder. Takes longer, obviously.
How do techs actually do all this partitioning and formatting?
In Windows, the main graphical tool is disk management. You can see your drives, create delete format partitions, assign drive letters, mount partitions into folders. Pretty powerful.
Is there a command line way?
Yep, disk part. Very powerful, good for scripting or recovery scenarios, but less intuitive than the DOA.
The source also mentions dynamic disks and RAID-like concepts.
Right. Windows has this concept of dynamic disks, which allows for more flexible volume configurations than basic disks you can create. Simple volumes, like partitions, span volumes combining space from multiple physical disks into one logical volume, striped volumes, RAID 0 data spread across disks for speed but no redundancy, mirrored volumes, RAID 1 identical data on 2 disks for redundancy.
And RAID 5.
That's striping with parity. Needs at least 3 disks. Offers a balance of speed, storage efficiency, and redundancy. If one disk fails, the data can be rebuilt from the others.
Is this the same as Windows storage spaces?
Similar concepts, but storage spaces is a newer, more modern software RAID feature built into Windows. It lets you pool physical drives and create virtual disks with different resiliency options. Simplino resiliency, mirror parity, separate from the older dynamic disks feature. It's generally more flexible.
Lots of options for managing multiple drives. What about basic maintenance, defrags?
Defragmentation is mostly relevant for older spinning HDDs. It rearranges file fragments so they're contiguous, speeding up access. Modern Windows usually schedules this automatically for HDDs. SSDs don't need defragging. They use a different process called trim to manage performance.
What about cleaning up junk files?
Windows has disk cleanup, and newer versions have storage sense, which can automatically delete temporary files, empty the recycle bin, etc., to free up space.
Common hard drive problems techs encounter.
Things like installation errors, wrong drivers, incompatible modes, data corruption leading to boot errors like boot mixers missing or blue screens, physically dying drives, clicking noises, slow performance, and issues with RAID arrays, drive failure, controller problems.
Okay, so storage is way more than just plugging in a drive. Connection, partitioning, formatting, file systems, maintenance, redundancy, lots to consider.
It's a critical piece of the puzzle where all your permanent data lives.
Right. Let's wrap things up by talking about keeping the whole system healthy and safe. OS maintenance and security.
Keeping things running smoothly.
What's job number 1 for maintenance?
Patching. Keeping the OS and applications updated. It's absolutely crucial.
Why? New features.
That too, sometimes. But mainly for security fixes. Developers are constantly finding and fixing vulnerabilities that could be exploited. Windows has quality updates, mostly fixes, and bigger feature updates, like moving from Windows 10 to 11.
Is this mostly automatic now?
Thankfully, yes, for most home users. Windows Update, macOS Software Update, Linux package managers usually handle it. But techs need to understand how it works, how to check manually, maybe how to schedule updates in a business environment to minimize disruption.
Installing applications seems simple, just click next, right?
If only. You need to think about compatibility first. Does it work with the OS version? Does the PC meet the hardware specs? Some apps need a decent graphics card, for example.
What else?
Consider the impact. How much disk space will it use? Will it drain the battery on a laptop? Does it use a lot of network bandwidth? And in a company, does it comply with organizational policies?
What does the install process itself often involve?
Running an installer file, .exe, .msi in Windows, .pkg, or dragging an .app file in macOS using package managers in Linux. You'll often see UAC prompts in Windows.
UAC, user account control.
Yep, those pop-ups asking for permission before making system changes. Sometimes you need to explicitly right-click and run as administrator. You agree to licenses, choose where to install it, maybe pick optional components. The process varies a bit by OS.
What about tweaking Windows for better performance?
There are settings for that. The source mentions performance options, historically in System Properties, now scattered a bit in the Settings app. You can adjust visual effects. Turning off animations can help older PCs feel snappier. You can also manage virtual memory, the page file, and configure DEP, Data Execution Prevention, a security feature.
So tune-ups are possible. Now something absolutely critical, backups.
Non-negotiable,
Yeah.
especially for personal data. You need copies of important files on separate media.
Separate media meaning?
An external hard drive or SSD, cloud storage like OneDrive or Google Drive, maybe a network-attached storage device. Backing up to a different folder on the same physical drive does not protect you if that drive fails.
Different types of backup.
The source mentions full, copies everything selected. Incremental, copies only files changed since the last backup, whether full or incremental. And differential, copies files changed since the last full backup.
Which is best?
They have trade-offs. Fulls take longest, but are simplest to restore. Incrementals are fastest to make, but potentially slowest to restore. Need last full plus all incrementals. Differentials are a balance. And always verify your backups work and practice restoring files occasionally.
Does Windows have built-in backup tools?
It does. There's the older backup and restore, Windows 7 feature, which can create system images. And System Restore is very useful. It creates restore points, snapshots of system files and settings, often automatically before installing software.
What does System Restore actually restore?
The system files, drivers, registry settings, installed programs. It's great for undoing a change that caused problems, but crucially, it does not restore your personal documents, pictures, music, etc. You need a separate backup for those.
So System Restore for system issues, proper backups for personal data.
Exactly. And for more advanced needs, lots of great third-party backup tools and services exist.
Okay, shifting to security. Starts with who can log in, right?
Right. User accounts. Two key concepts here. Authentication, proving who you are, usually with a password. And authorization, what you're allowed to do once you're logged in.
Password basics still matter.
Absolutely. Don't reuse passwords. Make them strong. Don't share them. All that fundamental stuff is still critical.
How does Windows control what users can do with files? NTFS permissions.
Yes. NTFS file system allows detailed permissions. Each file and folder has an access control list, ACL, saying which users or groups have which specific rights, read, write, modify, full control, etc.
Does it get complicated?
It can. Permissions can be inherited from parent folders, which is efficient but sometimes confusing. Understanding how permissions are applied and inherited is key to troubleshooting access-denied errors.
What about sharing folders over a network in Windows?
That uses shares. You can create standard shares on folders. Windows also has hidden administrative shares by default, like C for the C drive, or ADMINO, meant for remote administration. They're only accessible by administrator accounts. Securing those accounts is vital.
Encryption adds another layer, EFS.
Encrypting file system, EFS, is built into NTFS. It lets you encrypt individual files or folders tied to your user account's credentials. Only you can decrypt them.
Sounds good, but any downsides?
Big one. If you lose access to your Windows account and haven't backed up your EFS certificate, those encrypted files are gone forever. Unrecoverable. It's powerful but needs careful management.
User account control again, those pop-ups, why are they there?
UAC tries to prevent unauthorized changes. Even if you're logged in as an administrator, it makes you confirm actions that could significantly alter the system. Those shield icons on buttons are the clue it will trigger a UAC prompt. It's a safety check.
Annoying sometimes, but important.
Pretty much.
Yeah.
You can adjust how often it prompts, but disabling it entirely is generally not recommended.
Lastly, log files, where the system records what happened.
Exactly. Invaluable for troubleshooting. Windows Event Viewer, eventvwr.msc, lets you browse system, application, and security logs. Events are categorized by severity information, warning, error, critical, Often the first place to look when things go wrong.
Linux has something similar.
Yep, typically syslog, with logs often stored in varlog. Mac OS has its own logging system and keychain for managing passwords and certificates securely.
So keeping systems updated, backed up, secured with accounts and permissions, and knowing where to look in the logs. It's an ongoing process.
Constant vigilance, but essential for healthy and secure computing.
Wow. Okay. That was quite the tour.
Yeah.
From professionalism and troubleshooting through the hardware building blocks, CPU, RAM, motherboard, PSU.
Then the OS, peripherals, how data gets stored on drives.
Right. Partitioning, formatting, file systems, and finally, keeping it all running safely with maintenance, backups, security settings, logs.
It's a lot, but you see how interconnected it all is.
Definitely. It paints a much clearer picture of what's happening under the hood.
And remember, the goal isn't instant mastery of every detail. It's about grasping the concepts, knowing what's involved, and building that problem-solving mindset.
Like you said, knowing how to figure it out.
Exactly. The best techs aren't necessarily the ones who know everything offhand, but the ones who know how to find the answers and apply them systematically.
That's a really good way to put it. So to leave everyone with something to think about, we mentioned computers are everywhere now, right? Cars, fridges, whatever.
Embedded systems.
So think about a surprising place you've recently encountered some kind of computing device where you maybe didn't expect it. And how does understanding these layers, hardware, OS, storage, security, maybe change how you think about that specific device?
Ooh, good question. Or maybe think about it this way. Considering all those layers we discussed, which one do you think is ultimately the most challenging to keep secure and reliable? Is it the physical hardware, the complex OS, the way data is stored, or the user applications and permissions on top?
Interesting angle. Which layer is the trickiest link in the chain?
Yeah, something to mull over as you go about your day interacting with all this tech.
Definitely food for thought. Keep exploring these concepts.